This is section 8.5. Okay, so we're going to be talking about acid-catalyzed hydration of alkenes. Remember, hydration means we're adding a hydrogen and an OH group across the double bond here, such as in this reaction. And if you just have this alkene and you add to it some acid dissolved in water, which we term H3O plus because of the leveling effect that we learned about earlier in this semester, then you will have the Markovnikov addition product in very good yield, 90%. And because this runs using the Markovnikov mechanism of addition, we know that the reaction rate can really depend on the carbocation identity. So take, for instance, this table that is present in your book as well. And you can see that if you use ethylene, just C2 ethylene, and you run the same hydration reaction, you have some reaction rate, and we're going to call that our standard reaction rate. If you add just one carbon onto this ethylene to make propene or propylene, the reaction rate to isopropanol jumps immensely from 1 to 1,000,000. That is huge. So just having the ability for a secondary carbocation to exist is really huge for this reaction. Similarly, if you add another carbon to let the carbocation be tertiary, the reaction rate jump is enormous. That's 10 to the 11th, 11 zeros compared with 1. And again, please remember that these addition reactions are due to the stability of the carbocation that you're dealing with here. And the mechanism for this reaction is as shown here. As we just talked about, it's a Markovnikov cation that is formed after the pi bond in the alkene group deprotonates this hydronium ion. Once you have the carbocation formed, then the resulting water from that deprotonation performs a nucleophilic attack to make a different oxonium ion that then can be deprotonated by water to give you the neutral alcohol molecule. So this is also going to follow Markovnikov regioselectivity rules. But what's interesting about hydration of alkenes is that there's an equilibrium here that we need to think about. Because if you remember, in the eliminations chapter, chapter 7, adding concentrated H2SO4 to an alcohol allowed us to do an E1 type elimination to get the alkene back. So, starting from the alkene, if we use dilute H2SO4, it's still strong enough to make enough H3O plus to give us the alcohol. And if we wanted to get back to the alkene, we could simply concentrate the HSO4, remove some of the water to make the alkene. In the lab, in practical sense, what this means is if you have dilute acid, you can make the alcohol. And simply to get to the alkene, which is a dehydration, you need to make sure that there's not very much water around in the reaction. So either you use very concentrated acid or you use some special equipment that allows you to distill the water off as fast as it's made, basically. That way you only end up with the alkene. Alkenes are not the only molecules to undergo hydration either. We'll talk about that in a second, or I guess next section. But let's talk about the stereochemical outcome of hydration of an alkene. Because as we saw with hydrohalogenation, we're talking about the slow step being the formation of a carbocation that's planar. And once you form a planar carbocation, the nucleophile here, being water, can attack the carbocation either from the top face, here in red, or from the bottom face, in blue. And because there's no real impetus for this reaction to happen either way, you have an equal probability of both enantiomers happening, which means that your product is racemic. meaning in this example, you could get either one enantiomer or the other with the same probability. And this has been section 8.5.